So we talk about 2.1 rates of change and limits. We began here kind of our blitz review of everything we did last year in AP Calculus, and we'll do it in about 9 weeks here. So the limit as x approaches c of f of x equals L means that as x gets closer to c, the values of f of x, the y values get closer to L. And remember, what happens at c does not matter. It's irrelevant in terms of the limit. So a couple of examples, maybe starting on the far right, the kind of most natural thing is if you have a nice connected function, then we can see that as x approaches c from both sides, we come down the curve on the right and we come up the curve on the left, and we get closer and closer to that particular value of f of x or y, and that's what we mean by this limit existing and being equal to L. But it doesn't have to be that clean. Again, looking at these other two examples, it doesn't matter what happens at x equals c. The function could actually be undefined there, but the limit still does exist and is equal to L because the limit talks about what happens close to x equals c, not what happens at x equals c. And even if the function is defined to be something other than what it's approaching, that has no impact on whether the limit exists or not and what the limit is equal to. So in all three of these graphs, we see an example of the limit as x approaches c of f of x is indeed equal to L. We talked about our epsilon delta definition, and I just revisit this a little bit. So assume that f is defined in a neighborhood of c and that L is a real number. We say the function f has a limit as x approaches c if, given any epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon for all values of x that are within delta of c. So it goes something like you come up with whatever you want for epsilon, and so epsilon would be that distance from the limit point. So you might say, I would like to have all of the values of the function be within 0.5 of L, and then given that epsilon, then we would have a chance to say, let's look over here and say, oh, okay, as long as I choose all the x values to be within that delta of c, we will get y values that are within epsilon of L. And then you might choose a different epsilon, and that's fine. Then we get to find a different delta. So if you say, no, I want epsilon to be like 0.1. So if that limit really does exist, it should be that we can say at some point in time, all of the values of x within some range of c will produce y values within, say, epsilon equals 0.1 of L. And then we can say that's okay for that choice of epsilon. Then I'm going to have to tighten up what the delta is, and we'll say, that's going to be the delta that goes with that particular choice of epsilon. If you can do that for any choice of epsilon, you can find some delta so that all the values of x that are that close within delta of c produce y values that are within the given epsilon of L, then we say the limit does exist and is equal to L. So then the question becomes, well, when does a limit not exist? And there's three ways. So one is the right-hand limit different than the left-hand limit. So that could be, anything that might look something like this. Whereas you come in from the left, you approach one y value, and as you come in from the right, you approach a different y value. A nice example of an equation of something that the right-hand limit doesn't equal the left-hand limit. Sometimes it's nice to have these examples in your mind. That is going to be, if you remember our graph, that looks something like that. For all positive values of x, absolute value of x over x is just 1. So let me put in maybe an xy axis there. So there's the y-axis, there's the x-axis, and this is a y value of 1, that's a y value of negative 1. So any positive number you plug in for x, we get absolute value of x over x is equal to 1. Any negative value, absolute value of x over x is negative 1. And if you plug in 0, we get 0 over 0, which is undefined. So this is what the graph of that function looks like, and that is an example of where the limit as x approaches 0 of that f of x we say does not exist, and we are welcome to abbreviate that as DNE. Another example would be infinite, so you can think any kind of vertical asymptote. So for example, if we got something like our volcano function, that would be an example where the limit as x approaches c of f of x does not exist as well, because it's not getting closer and closer to a single number. It's growing large without bound, and so that means the limit doesn't exist. Another example of one where it doesn't exist, our classic example here, and it's hard to come up with too many different ones where this kind of thing happens, but our classic example is sine of 1 over x. So what happens here is as you approach 0, this thing just starts to go crazy, and likewise as you come into 0 from the left. And so the idea is no matter how small a region, how small a little interval around 0 you pick, is going to contain an infinite number of those sine waves that going up to 1 and back down to negative 1. And so that is our third way that a limit can fail to exist. I'm going to go to a new panel here and talk about one-sided limits. This is an idea, and just to remind you of our notation a little bit as well. So I'm going to talk about, this is called the greatest integer function, this kind of weird notation there. And what that means is it's the greatest integer less than or equal to the number. So for example, the greatest integer of 2 is equal to 2, because 2 is the greatest integer less than or equal to 2. The greatest integer of, say, 3.3 is going to be equal to 3. It's the greatest integer less than or equal to 3.3. So in terms of a graph, what we get looks something like this. So the greatest integer of 0 is 0, and 0.1, 0.2, 0.3, all the way up to here is the greatest integer less than or equal to that number is going to be 0. Then once we get to 1, it jumps up here to 1, because now the greatest integer greater than or equal to 1 is 1. And we do something like this, and it goes on forever and ever. It works also in the negative direction. So you get this. Sometimes this is also called, so it's called the greatest integer function. And that's the notation you see, the way that it's denoted. And it comes up in our book fairly regularly. So that's the greatest integer function. It's sometimes referred to as the step function because it kind of looks like steps going up there. So it gives us also a chance to talk about, what is the limit as x approaches, say, 3 from the left. So there's our notation. So this refers to a left-hand limit, and that's also an abbreviation for that. LHL is universally accepted. So we have 1, 2, 3, and let's do one more of those. So you can see kind of from the graph, as you approach 3 from the left, as you plug in values of x that are less than 3 coming in this way, then the greatest integer function is going to be giving you these values in here, which is going to be 2. So we would say that's limit as you approach 3 from the left, or the left-hand limit, is equal to 2. And in a similar way, the limit as x approaches 3 from the right of that greatest integer function would mean as we come in now from the right side, that is using values of x that are a little bit bigger than 3, then all of these are going to be giving us a value of 3. And since the left-hand limit is 2 and the right-hand limit is 3, then we would say the limit as x approaches 3 of that greatest integer function does not exist, because that left-hand limit is different than the right-hand limit. So we also talked back in the day about what we called the sandwich theorem or squeeze theorem. I think our book last year called it the squeeze theorem. I think our book this year likes sandwich. So these refer to the same idea. And the idea is that if we know that g of x is less than or equal to f of x, which is less than or equal to h of x, for some neighborhood containing c, for some neighborhood containing c, and if we know that the limit as x approaches c of g of x is equal to the same limit as x approaching c of h of x. So if the bigger or the smaller function on the left approaches the same value as we approach c as the bigger function on the right, then our conclusion is that the limit as x approaches c of f of x gets squeezed or sandwiched and must also be that same value L. So here's kind of a nice example, a little different one than we did last year. Let's say our f of x is going to be this kind of exotic function, x sine of 1 over x. So sine of 1 over x is our oscillating function there. I'll give you a quick look at what the graph is. So the sine of 1 over x, without the x in front of it, is that function that does this crazy oscillation. Now, if we put in the x in there as well, so once we add in this x, then that's sometimes referred to as a damping function. So it's going to damp down those oscillations. So sine, we know, is bouncing around between 1 and negative 1, but y equals x, we know, is going to look like a 45-degree angle through the origin. So the biggest that sine can be, and no matter what you plug in, is 1, and the smallest it can ever be is negative 1. So if we graph y equals x, and that's y equals negative x, and this is y equals x, then all those values where sine of 1 over x were equal to 1 is now going to get multiplied by that x, and so that's going to put those points right on the line y equals x. And all those values where sine was equal to negative 1 are going to multiply by that x, and it's going to put those points on the line y equals negative x. And so now our function is still going to oscillate crazily, but it's going to get squished in there and forced down into the origin. So what we can do in terms of kind of thinking as using our sandwich theorem is we know that x sine of 1 over x is less than or equal to x times 1, because the biggest sine can be is 1 no matter what you plug in for it. And it's going to be greater than or equal to x times negative 1, because the smallest that x can be, that sine rather can be, is negative 1. So what we have then is negative x is less than or equal to x times the sine of 1 over x, which is less than or equal to x. And we're interested in what is the limit as x approaches 0. So we can see that as x approaches 0, this negative x is going to approach 0, and we can see that this x is going to approach 0, and we have sandwiched or squeezed our x sine of 1 over x into 0, as we can see in the graph here. And so we can then say then that the limit as x goes to 0 of x sine of 1 over x must indeed be 0 from our sandwich or squeeze theorem. Okay, I'm going to go one more panel. Let's remember our instantaneous rate of change. It's been a little while. So instantaneous rate of change, we know is given by the limit as h goes to 0 of f of x plus h minus f of x all over h, and we hopefully recognize that as also our definition of the derivative. So I'm going to stop this for a minute and write down an example, and then we'll come up back and we'll walk through it here. This will just take a second. So here's our question. If we drop a ball from a platform 100 feet above the ground, the position at time t is given by h of t equals 100 minus 16t squared. So our first question is find the average speed for the first 2 seconds. Now, it's been a while, but remember, speed is equal to the absolute value of the velocity. So our velocity is going to be just our average rate of change. So it's our difference quotient, like we see up here, only without the limit. It's also the slope formula. So we're going to say that our velocity would be h of 2 minus h of 0 all over 2 minus 0. Then to make it speed, we would just plug it into our absolute values. So the h of 2 is going to be 100 minus 16 times 4 is 64. So that is our h of 2. And minus the 0 is going to be 100. And all over the 2 minus 0 is 2. And that's going to still be in absolute values. So 100 minus 64 is 36. We have minus 100 over 2 in absolute values. 36 minus 100 is a negative 64. And so that'll be a negative 32. And when we take the absolute value, our speed is going to be 32. Now the units on that are going to be this change in height over the change in time. And so for us, that's going to be in feet per second. So the units on an average rate of change are going to be feet per second, or distance per time. Now the speed right at t equals 2, now that's an instantaneous rate of change. So we still have the speed is going to be the absolute value of the velocity, but our velocity is going to be, and now we're going to come back to our definition right up here. This is going to be our instantaneous rate of change. So we are going to take the limit as h goes to 0. And let's do, since we want it at 2, the value, we have x here, but our variable is going to be t. So let's call that f of 2 plus h minus f of 2 all over h. And then after we get this, we're going to take, this will be our velocity, so we'll take its absolute value. So that is going to be our 100 minus the 2, I left off the 16, hold on. 100 minus 16 times 2 plus h squared minus the 100 minus 16 times 2 squared all over h, and we're going to take that limit as h goes to 0. So that's going to be 100 minus 16 times, the first one squared is 4, twice the product is 4h, second one squared is h squared, and we're going to subtract, that's 100 minus 4 times 16 is 64 again. That's still going to be over our h, and we're still taking the limit as h goes to 0. So let's see, we've got the limit as h goes to 0. That's going to be 100 minus 16 times 4 is 64. 16 times 4 again is going to be a minus 64h and a minus 16h squared. And 100 minus 64 was 36, so that's a minus 36 all over h. So we can see 100 minus 64 is 36, and that's going to cancel with the negative 36. As we have seen many times before, anything without an h in it should cancel, and it has. We can then factor an h out of the terms that remain. Negative 64 minus 16h, that's all over h. Once we cancel the h, we're free to let the limit go to 0. We just direct substitute in the 0 for the h, and we're going to get negative 64 for the instantaneous velocity, and so the speed will be the absolute value of that negative 64, which is 64, and that is also going to be in feet per second. So instantaneous rate of change and average rate of change have the same units. All right, very good.